All right, there we are back again for the B lecture of week 6 of our course. So let's dive straight into it. What's on the agenda? As always, I start with a recap. What have we learned? And then we'll delve a little bit deeper into what we have learned so far with categorical variables. What we learned is that we can use dummy variables. So I'll elaborate a little bit more on how to work with those dummy variables. And then we'll discuss the most mathematical part of this course. We'll discuss a couple of mathematical transformations because that's going to be super important for the last week of the course, that we understand what things like exponentials and logarithms, what those kind of transformations, what they mean and what they do. And then we'll close off with a few more elaborations on probabilities, odds, and a new concept, so-called log odds, and how they relate to each other. So what did we learn in the A lecture? We learned that we can in fact include categorical X variables into our multiple linear regression models, and the way to do that is to use dummy variables. And that's great. That means that we can analyze variables that are not strictly continuous. So that might be categorical, even ordinal. We have also started with considering, well, okay, that's for X variables. What about if my Y variable is categorical? So if my dependent variable is a categorical variable. And yeah, I already told you that yes, we can actually do that. But we are going to have to take that step by step. So first we have to be very much aware of some of the basics. So we have to understand really well what probabilities, odds and odds ratios are. So what were probabilities? Well, probabilities are a measure of how likely is it that something happens, some event takes place. And that event is the thing that you're trying to analyze, that's your dependent variable. So that could be whether people voted or not, or whether countries are at war or not. And so how do we calculate this? How likely is it that something happens? Well, you look at how often did it happen, and you divide it by how often could it have happened. So in other words, you take the number of events and divide those by the number of observations, and that will give you your probability value, your value for the probability. So that tells us something about how likely it is that something happens. We've also seen that if we take a variable and we use dummy coding on that variable, so we assign those observations the value 0 that did not experience the event, of which the event did not occur, and we assign the observations for which the event did occur, so those observations that did experience the event, then if we were to calculate the mean of that variable, that's the same thing as calculating the probability that the event happens for that variable. So we already saw that this is in fact the case as long as we use 0,1 dummy coding for the variable. Taking the mean is the same thing as calculating the proportion of observations in which the event took place or happened, and that's identical to the probability that the event happened in our set of observations, and that's something that's going to come in useful later. Probability tells us something about how likely is it that something happens. We can also look at, well, how likely is it that something happens compared to how unlikely is it that something happens, and that's what we mean when we talk about the odds of something happening. So the odds are a statement about how relatively likely is it that something happens compared to how relatively likely is it that something does not happen. So given that the probability signifies how likely it is that something happens, well, how would you then calculate the odds? Well, it is the probability that something happens divided by the probability that that same thing does not in fact happen. Yeah, so the probability that the event occurs divided by the probability that the event does not occur. In other words, the probability of the event happening divided by 1 minus the probability, because of course the probability that the event does occur plus the probability of that the event does not occur. So if you sum those two probabilities up, of course you should get the value 1, because then we would be covering all possible states of our observations. So once you know the probability that the event happens, you can simply calculate the probability that the same event does not happen by saying, well, that's 1 minus the probability that the event happens. So the odds are p divided by 1 minus p. And we also looked at how we can look at a measure of association, the so-called odds ratio, which expresses the relationship between two variables as ratios of these odds, of how relatively likely is it that something happens compared to how likely is it that that same thing does not happen. So we saw that the odds ratio indicates a change in the odds that some event occurs with a 1 unit increase or change in some x variable on its scale. And we looked at a very simple example where there were just two categories on the x variable, where people were either employed or unemployed. So then there's just one step that we can make on that scale. And we saw that then we can simply calculate the odds ratio of the thing that we want to analyze, that we want to explain, the event that we want to explain for both of these categories, and then divide one by the other, and then you get a ratio of odds. So an odds ratio that tells you how many times larger are the odds for the event happening for the one category compared to the other category. More in general, we can extend this logic over to x variables with more than one category, even continuous x variables, and then the odds ratio signify, well, how many times larger do the odds become with a 1 unit change on our x variable. So that's what we learned so far. Now let's delve a bit deeper into categorical data analysis, and specifically let's talk a bit more about something that is in general a very useful skill in life, and specifically when you do statistical research, it is working with dummies. So there's a couple of things I want to delve a bit deeper into because they're going to be important to you. So one thing is that you're often in a situation that you have some x variable that you want to include in your model, which can be broken up into different numbers of categories. So you can break it up into 2 categories, but maybe you could also break it up into 3 categories or 4 categories or 5 categories. And it can sometimes be useful to create more categories than you would theoretically strictly need. So sometimes maybe your hypothesis, a very simple hypothesis about just the difference between one category compared to another category. But even if that's the case, sometimes it might make sense to split your categories up further than just into those categories, if you have sufficient observations within each of these categories. So if you have so many observations within each of those categories that you are confident that yes, you can get some reliable estimate of a regression coefficient for that for the category that we are analyzing. So if you have sufficient data, sufficient observations within those categories, sometimes it can be useful to split your x variables up into more categories than you strictly would need based on your theoretical hypothesis. So to provide an example, we might want to test that the hypothesis that religious people have more trust in parliament than non-religious people. And let's suppose we want to do that with data from the Netherlands, and our questionnaire survey didn't just recorded whether people were belonging to a religious denomination or not, but it actually recorded which religious denomination people belong to, as the European Social Survey does, in fact. And then you could say, well, I could just make one dummy variable for whether or not people are religious, but I would also split up that religiosity category in multiple subcategories. For instance, a subcategory for those that are belonging to a Catholic denomination, and for those that belong to a Protestant denomination, or for those that belong to other types of religious denominations. So notice now we have actually created 3 dummy variables. So we actually created 4 categories on our religiosity variable. So non-religious, Catholic, Protestant, and other. Even though our hypothesis only requires 2. But should you ever do that? Well, yes, sometimes it can be useful to do that. So, for instance, if we would test this hypothesis for the Netherlands, now if you have a bit of theoretical understanding about differences in religiosity in the Netherlands, you know that there are, for historical reasons and also for religious reasons, quite substantive differences between the Catholic denomination and the Protestant denomination. And of course, those might be quite different again to many other denominations. So you might want to actually still be able as a researcher to be able to see those potential differences. And of course, the only way we can still see those differences is by still allowing there for there to be differences. So we could create more categories in this case than we strictly need based on our hypothesis. And as long as you have sufficient numbers of observations within each of those categories, so there's really a large number of Catholics, a large number of Protestants, and a large number of other religious denominations that are there in your data set, then you could do that. So that gives you more information, because you're allowing there still to be differences between these different religious denominations. Yeah, so that can sometimes be quite interesting, yeah, because otherwise you're basically throwing away all the information that distinguishes between different types of religiosity, and only know about, yeah, it's the difference between religious or not religious people, but there might be quite a lot of differences within those religious peoples going on, depending on the different denominations. Yeah, so that sometimes can really make a lot of sense. But notice now that we would actually have one theoretical hypothesis, but 3 regression coefficients that we would be testing. So in that case, what would formally be the null hypothesis that we would be interested in? Well, given that we only expect an effect of religious people, yes, compared to non-religious people, the null hypothesis that we formally would be testing is that there is no difference between the Catholics and the non-religious, and that there is no difference between the Protestants and the non-religious, and there is no difference between the other religious denominations and the non-religious in the population. In other words, the null hypothesis that we then theoretically would be testing is the null hypothesis that our regression coefficient for the Catholic dummy B1 is the same value as our regression coefficient for the Protestant dummy B2, is the same regression coefficient as the B3, the coefficient for our dummy variable for other religious dominations, and all of those are the value 0. Yeah, so we're assuming that all of those regression coefficients take the value 0 in the population, because that would indicate that there are no differences in the populations between any of those religious denominations and the non-religious people. Yeah, so if you were to split up these categories, you would need to take into account that what you're really trying to test in that case is the null hypothesis that all these coefficients are 0 in the population. Well, this probably looks familiar to you if you've been paying attention, but what we're doing here would be, we would be requiring a multi-parameter test, because you're testing multiple regression parameters at the same time. And the parameter for the B1 and B2 and B3 regression coefficient. Yeah. In that case, it is recommended that you don't just look at the individual t-tests for each one of those dummy coefficients, so the t-test for B1 and the t-test for B2 and the t-test for B3, but actually really do a multi-parameter test as well, where you would estimate a model without each of these 3 dummy variables included, and a model with these 3 dummy variables included, and then get the F change statistic, and also take a look at the p-value that's associated with that F change test statistic. Yeah, so use an F test to compare the model with and without all of those dummy variables that belong to that independent variable to have an overall test of whether or not you can reject the null hypothesis that all 3 of those coefficients, or however many categories and coefficients you are working with, whether all of them are jointly different from 0, whether we can jointly reject the null hypothesis for all of them. Yeah, so that's one thing that is definitely recommended, that if you have multiple dummy variables and therefore coefficients that all test the same underlying theoretical hypothesis, well, also do this multi-parameter test and take a look at the p-value for that F test. Either way, whether you're looking at individual p-values for the individual t-tests, or you're looking at the overall f-test for all of the dummies combined, there is one thing you need to be aware of. There's one added difficulty that is going to arise once we start comparing multiple groups with each other. And I think at the end of the last lecture I already included this nice comic, again stolen from the website from XKCD. And the point of this comic is now going to become very relevant. What happens to our p-values when we start comparing multiple different groups, when we start to look at multiple different p-values, do multiple group comparisons for testing basically the same underlying theoretical hypothesis? Well, let's just remind ourselves, when we do statistical hypothesis tests, in the sense that we say, well, we have some kind of null hypothesis and we pick some kind of significance level alpha, then, well, what does that alpha level reflect? It is basically the probability that we choose. Yeah, so it reflects the chosen probability that we choose of rejecting our null hypothesis if it is actually true. In other words, if we reject the null hypothesis while it's actually true, in other words, saying, well, there is a statistically significant effect while there is none. So this is basically how willing are we to make a so-called type 1 error when we say that there is an effect, when as a matter of fact there is no effect. Yeah, so that is what the significance level alpha actually reflects, right? It is the idea that we as researchers, based on how much data do we have and how large we assume the effects to be, we pick a significance level alpha that helps us make a decision about whether or not we can reject our null hypothesis. And how do we do that? We say, well, how willing are we to incorrectly reject the null hypothesis? How willing are we to say, well, we have an effect, while in fact there is no effect? So how large do we want to make the probability of that happening? So how large do we want to make the probability of making a type 1 error? Yeah, so in other words, so for instance, if we would be working with this standard alpha level of 0.05, what does it mean when we say we pick an alpha level of 0.05? It means that we expect to find a result of a significant effect when there actually is no effect in the population 5% of the times. So that's how willing we are to find significant effects when they actually are none. Yeah, so if we say we work with an alpha of 0.05, that means that we are willing to run a 5% risk of finding a significant effect when there really is no when there is no effect in the population at all. Yeah, so that's the risk that we are then running. So or in other words, thinking about that, well, what does it mean, a risk of 5%? Well, this is always in relation to what would happen if we would take all possible samples from our population. So for instance, let's say that we pick an alpha of 0.05. That's the same thing as saying we would, for instance, be willing to accept that in 5 of 100 possible samples that we take from the populations, we find an effect when there actually is no effect. So that's how willing we are to risk that. So that's what the alpha level represents, right? How willing are we to accept that we get a significant effect in our specific sample under the assumption that there actually is no effect at all in the population. So alpha 0.005 means that we are willing to risk that in 5 of 100 possible samples, for instance. Right. Now we have a problem, because this assumes that our statistical tests are independent from each other. But now we have a situation where we have multiple different statistical tests that are not independent from each other. Yeah, so if, for instance, we say, well, we have one theoretical hypothesis that we want to test, that's whether religious people have more trust in parliament or government than non-religious people, but we're actually creating 3 different dummy variables to distinguish between different religious denominations. Then we actually have 3 statistical tests, the 3 t-tests for each of these regression coefficients, or the overall f-test, which again is a test of whether any of those categories deviates from is significantly different. So in either case, what we're basically having now is a statistical test that's not independent, that we're basically having multiple tests that we are combining to make one conclusion about the same underlying theoretical hypothesis. And that's problematic. Because if you think about these the different t-tests for the individual regression coefficients, for instance, well, we get one t-test that will have some p-value associated with it. And then we get a second t-test for the second regression coefficient that has a p-value associated with that. And then we can take a look at each of these tests, and individually we might say, well, if the p-value is smaller than 0.05, we are willing to reject a null hypothesis because we're working with an alpha of 0.05. But now for each additional test that we are doing, we're basically doubling the risk of incorrectly rejecting our null hypothesis, because we're just adding one new test that again has another 5% risk of incorrectly rejecting the null hypothesis. So for each additional test that we are doing, we are basically multiplying doubling the true risk of incorrectly rejecting our null hypothesis. Yeah, so if we work with an alpha of 0.05, assuming that, and we have 2 different statistical tests that we are combining, then actually just looking at, well, is the p-value smaller than 0.05 coincides not with risking that we have a significant effect in 5 out of 100 possible samples, but in 10 out of 100 possible samples. So we're basically doubling the risk of making a type 1 error. This is referred to often as a inflated type 1 error rate. So just doing what we usually do for looking at the p-values, and then if the p-value is smaller than our chosen level of significance, so our standard alpha level, if we would just be doing that, we would actually have a much larger type 1 error rate than implied by the 0.05. It would not be 5%, it would be higher than 5%. So that's what is referred to as an inflated type 1 error rate. Now, there are a couple of different solutions that you consider for this, and I'm going to discuss one of them because it's quite often used and it's fairly straightforward, and none of them are perfect, but this one is at least helpful in many situations, and this is so-called Bonferroni adjustment to your statistical test, named after mathematician Carlo Emilio Bonferroni, who worked on some mathematics that gave rise to this adjustment. So how does it work? Well, the idea is that look at how many statistical tests you're carrying out that are not independent from each other, so that test the same underlying theoretical hypothesis. Yeah, that number of tests we're going to say that's K. This K is going to signify how many tests we are carrying out. And then if you want to reach let's say a true alpha level, your true alpha level, then whatever alpha level you want to work with, divide that by the number of tests that you are doing, and use that new alpha level as your level of significance, as your significance level, because then basically we are bringing back down the type 1 error rate to where it should be. Yeah, remember, for each additional test, you're basically doubling the type 1 error rate. So the logic is, well, then just divide your alpha level by the number of tests that you're doing to bring it back down to the level where it's supposed to be. Yeah, so in our example, if we say, well, we want to test a theoretical hypothesis that religious people have more trust in parliament than non-religious people, but we're actually splitting up these religious people into 3 different categories, Catholic, Protestant, and other, because we want to still be able to analyze differences between these two different groups, then you could say, well, great, but that means that we're actually doing 3 statistical tests for the same underlying theoretical hypothesis. Yeah, so we have our test of the B1 coefficient, the B2 coefficient, or the B3 coefficient. So that means that we have 3 tests for one hypothesis that really justly has an effect on trust. So what is the number of tests that we have? What is the number for that we have to plug in for K? It is 3 in this case, because we have 3 statistical tests. So if you want to work with an alpha level of 0.05, so you want to incorrectly run the risk of rejecting your null hypothesis 5% of the time, so in 5% of the possible samples, well, then simply divide that alpha value of 0.05 by the number of statistical tests, so by 3, and use that alpha level instead for your hypothesis test. Yeah, so which works out to an alpha level of around about 0.0167. So in that case, you would say, well, when would you then reject the null hypothesis? Well, only if it is smaller than this new alpha level of 0.0167. Yeah, so this is then how you can make that decision. Again, of course, as always, there is nothing magic about 0.05. This is not a light switch where we can say it's magically becoming statistically significant or insignificant. It's just a helpful tool for you to reach a decision about your theoretical hypothesis. But now at least you understand that, yes, but if I have multiple tests, I need to be aware that I am blowing up the type 1 error rate. So if I want to get to a same kind of alpha level to make a judgment, or have as a guideline to make a judgment, then one way of bringing back down the type 1 error rate is by dividing by the number of tests. Yeah, there is a downside to that. Of course, the more likely you make it to not reject, the more difficult you make it to reject your null hypothesis, the more likely you make it to not be rejecting your null hypothesis when you should be rejecting your null hypothesis. In other words, by using this Bonferroni adjustment, we make it more difficult to find a statistically significant effect. But of course, that also means that we make it more difficult to find a statistically significant effect if in fact there really is an effect in the population. So in other words, using this Bonferroni correction to our statistical test is what is called a conservative test that we're then doing, in the sense that it leads to an increase in the type 2 error rate. So what the type 2 error rate is when you say, well, there is no effect, I'm not able to reject the null hypothesis, when as a matter of fact you should be rejecting the null hypothesis, because in the population there really is an effect. Yeah, so in that sense there is always a trade-off with these kind of corrections that we can make to our significance levels, that if you do it in such a way that you are decreasing the risk of a type 1 error by definition, you're going to increase the risk of a type 2 error and vice versa. So this is always the trade-off that we need to make. Yeah, so be aware of that Bonferroni adjustment is great in the sense that it allows you to think about, okay, how could I bring back down the type 1 error rate so that I'm not so likely to say, well, it's significant. Well, I shouldn't be saying that it's significant, statistically significant, but at the same time, that also means that you have a larger risk of not saying that there is no effect or that you find no support for an effect. As a matter of fact, there is actually an effect. Yeah, that's always a trade-off that we have to make. A second thing I want to discuss on working with dummies is, well, we discussed interaction models last time around. And, well, when we discussed these interaction models, we assumed that our independent variable and our moderator variable were both continuous variables. So what happens if one if one of our x variables in an interaction is a categorical variable? So let's consider that. So for example, let's say we have the hypothesis that the effect of income on satisfaction with government is bigger for women than for men. So in this case, we would say, well, we have a continuous independent variable, income, but we have a moderator variable, gender, which is in this case measured in just 2 categories. So it's a categorical moderator variable. Or maybe we have the hypothesis that the effect of age in trust in parliament is smaller for middle class people than for lower class people, and that it's also smaller for higher class people than for lower class people. So basically saying, well, age makes more of a difference for lower class people than for middle and for higher class people. Yeah, all of these are hypotheses that you might want to test because your theory predicts these things to be the case. But also in this case, you see, well, if we treat age as a continuous variable, but we now have a moderator variable, social economic class, where apparently we distinguish between 3 different categories, lower, middle, and higher class. So, that means that we have a moderator variable that's actually categorical. So it is actually quite common to have these situations. And the good news is it's actually a bit easier to interpret these interaction effects than just interaction effects with 2 continuous variables, as I will show you. And the other good news is because we have dummy variables for our moderators in this case, there really is no need to center those variables. Remember, centering is basically, mean centering is basically shifting the zero of our variable to where the mean value used to be of the original variable, so that we can create a meaningful 0 point on the scale of that variable, because that makes the main effects in our interaction model just so much nicer and easier to interpret. Well, if we talk about dummy variables, we already have a very nice interpretation for the 0 value, because that's just the value for the reference category. So for dummy variables, it is not necessary to mean center. You can just use the original dummy coding if you have dummy variables as part of your interaction term. Yeah, so let's walk through a completely fictional example. So I completely made up these regression coefficients here, but let's say I wanted to look at what is the effect on trust in parliament. So I shortened this to TIP here so that it fits on the slide. Of age, but also, well, but to what extent is that moderated by difference in socioeconomic class? So to what extent does the age effect differ between people of lower, middle, and higher and then the higher socioeconomic classes? Yeah, so let's assume that this is the regression model that I then estimated. Notice, of course, that I have a constant value, 6.0 in this case. I get the main effect for age, 0.6. Then I get a main effect for the middle income people, because I picked lower class as the reference category. So I get 1 dummy coefficient for the middle class. That gives us the main effect for the middle class. I also have, of course, a dummy coefficient for the higher class, because that gives us the main effect for the higher class people. And I get 2 interaction terms, one where I'm interacting age with the middle class dummy, and one where I'm interacting age with the higher class dummy. So the entire regression model then gives us 6.0 plus 0.6 times age, plus 0.5 times middle class dummy, plus 1.2 times higher class dummy, plus 0.5 times age times middle class dummy, minus negative coefficient in this case, 0.2 times age times the higher class dummy plus an error term. Yeah, so that's a fictional example of the kind of regression estimates that you can get. Yeah, so again, I picked lower class as the reference category. So they are nowhere in the model. But age is in there, and middle class and higher class is in there. So that's the main effects. And we have 2 interaction terms because we have 2 dummy variables, one for middle class and one for higher class. So we need to create an interaction term for both of those to allow the age effect to vary across all the 3 different classes. So let's walk through that step by step. Let's just start with the reference category. Well, the reference category that I picked here is lower class. So what is now the effect of age for people that are in the lower socioeconomic class? What is the slope of that regression coefficient for age? Well, let's walk through the formula. We have trust in parliament equals 6.0. Well, that's the constant. That's the same for everybody. Plus 0.6 times age. So that's the age effect. Plus 0.5 times the middle class dummy. But the lower class people are not middle class people. So they get a value 0 on the middle class dummy. So in other words, we would multiply the regression coefficient 0.5 times 0. Multiply something by 0, the result is 0, and you can drop it from your equation because it doesn't add anything anymore. And the same is also true for the higher class dummy, because lower class people are not higher class people. So these people would get the value 0 for the higher class dummy as well. So also this regression coefficient of plus 1.2 would be multiplied by 0 for these cases. And therefore the result would be 0, and we could drop it from the equation. The lower class people are also not middle class people, so the interaction term of middle class with age would also work out to 0. Why? Well, because the middle class dummy would take the value 0 for these cases. So you would get 0.5 times age times 0. Well, multiply something by 0, you get 0. So it's 0.5 times age times 0, which works out to, well, that's just 0. And again, we can also drop this interaction term from the model because it doesn't add anything for this class of cases. And the same is also true for the last interaction term, because these are lower class people, therefore not higher class people. Therefore they get the value 0 on the higher class dummy, which means that we would also multiply this minus 0.2 times age times 0. Well, multiply something by 0, you get 0, and you can drop it from the equation. So in other words, well, what is the slope coefficient of age for the lower class people? It is the main effect of age. It is 0.6. So whenever you have these interactions with categorical moderator variables, the main effect gives you the slope for the reference category. So this is useful to know. You can also look at what would be the predicted value for the lower class people. Well, it would be 6.0, the constant, because it's the same for everybody, plus 0.6 multiplied by the value of age of these people. That's how we could calculate the predicted value for the lower class people, because all the other parts of the formula are not relevant for the lower class people, because all of them would be multiplied by 0, because they get a 0 on those dummy coefficients of middle and higher class. So all of the other things basically are not relevant for the lower class people. Well, we can do the same thing for the middle class people. Well, what would be the slope coefficient for people in the middle class? Well, again, we start with the constant of 6.0. That's the same for everybody. We have the main effect of age 0.6. That's also the same for everybody. The middle class dummy is relevant for the middle class people because they get the value 1 on the middle class dummy. So we have to leave the plus 0.5 times middle class in the model. But the higher class dummy will get the value 0 for middle class people because they are middle class people, not higher class people. So that value on the higher class dummy is going to be 0. So this plus 1.2 regression coefficient would be multiplied by the value 0, which works out to 0, which means we can drop that part from the formula. And also at the very end, we can drop the second interaction term where we're interacting age with the higher class dummy, because again, the higher class dummy takes the value 0 for middle class people because they are not higher class people. So also this part of the formula would work out to 0 and can be dropped. We do still have the interaction term for the higher class people present in the model. So that's the plus 0.5 times age times middle class. And the middle class dummy for these people will take the value 1. So what do we have here? We have two effects for age that are present in our model. The 0.6 from the main effect. So that is the effect that we got for the lower class people. But now we have a second age effect present in our model, plus 0.5 times age, which is the effect for the middle class people, because that multiplied by 1 is just 0.5 times age. So hopefully you remember from last week when we are doing the simple slopes analysis that if you have two regression coefficients in the same model about the same variable, and there is nothing else happening, it's just two regression coefficients that are about the same variable, then we can just add up these two regression coefficients into one single coefficient to give us an effect. So in this case, we have now for the middle class people two coefficients, 0.6, the main effect, and 0.5, the interaction effect, which basically tells us, well, how much higher is the slope coefficient for middle class people than for just the lower class people. So we can just add up this 0.5 to the 0.6 that we have as the main effect, and it works out to a value of 1.1. So in other words, the slope coefficient of h for the middle class people would in this case be 0.5 higher 0.5 higher than the slope coefficient for the lower class people, and that means that the slope coefficient for the middle class people is 1.1. And again, we could take a look at the predicted value for the middle class people as well. Well, what is that? Well, that's 6.0, the constant, that's the same for everybody, plus a second constant value due to the main effect for middle class that we have in our model. So basically that is allowing the intercept to also be of a different value for the middle class people. Again, look back at the simple slopes analysis that we did in the B lecture last week to understand why it's really important that we do allow for the intercept to be different for the middle class people in this case than for the lower class people. But for middle class people, well, they score a value 1 on the dummy variable middle class, so that's 0.5 times 1, so that just works out to 0.5. So in other words, the predicted value for middle class people works out to 6.0, the constant, plus what we add to the constant for the middle class people is 0.5, plus 1.1 times h, so that's the effect of h for people in the middle class, which works out to 6.5 plus 1.1 times h. And we can do, of course, the same thing again for the higher class people. We can look at, well, what is the slope coefficient of h for the higher class people? Again, just run through the formula and fill in what you can fill in. So 6.0, that's the same for everybody. 0.6 times h, that's also the same for everybody, the main effect of h. Plus 0.5 times middle class, that's the coefficient for the middle class dummy. Well, now we're considering people in the higher class. So they are not middle class people, so they get the value 0 for the middle class dummy. In other words, we can drop this part from the equation because multiplying by something by 0 gives us 0. They are higher class people, so the plus 1.2 times higher class, that remains in the model. So that's for those people, it's plus 1.2 times 1 because they score the value 1 on the higher class dummy. But we can also drop the interaction term of h with middle class because the middle class dummy takes the value 0 for these higher class people because they are not middle class. So that's 0 times 0. Times h times 0.5, that works out to 0. So we can also drop that from the equation. But yes, and the last part, so the interaction of h with the higher class dummy, that is of course still relevant for this specific set of observations, these higher class people, because the higher class dummy for these people takes the value 1. So that's minus 0.2 times h times 1. In other words, that's minus 0.2 times h. In other words, again, we have a situation where we now have two effects for h in our model, the plus 0.6, the main effect, and the minus 0.2, that's given by this interaction term for the higher class people. So again, if we have two effects, we can just add for the same x variable and nothing else is happening, we can just add those two effects together. So in this case, we have the main effect of 0.6 minus 0.2 for how much lower, in this case, that h effect is for the higher class people compared to the lower class people, which works out to a slope coefficient of h for the higher class people of 0.4. Yeah, so for them, the slope coefficient of h is 0.2 lower than for the lower class people, which works out to a slope coefficient of 0.4. And again, we can calculate the predicted value also for the higher class people. It's 6.0, the constant, plus 1.2, so that's the main effect for the higher class dummy. So now we're adding a constant value of 1.2 for the higher class people. Yeah, basically again allowing the intercept to be at a different place for these higher class people, plus the effect of h that we have in our model for the higher class people, which works out to 0.4. In other words, the predicted value for higher class people can be calculated by taking a constant value of 7.2, so that's 6.0 plus 1.2 works out to 7.2, plus 0.4 multiplied by the value of h for these higher class people. That's something you have to work through yourself sometimes to really get the hang of it. But once you know it, it's really easy to interpret these interactions with categorical, with one categorical variable. Well, what if both our x variables are categorical? So if both our independent variable as well as our mediator is categorical, of course that might also happen, might also be theoretically interesting. So again, I'm showing you a fictional example here. So I completely made up the numbers just that we have some example to work with. So let's say I wanted to look at the interaction between gender and class. Look at how the effects for gender might be different across different classes, or vice versa, how the class effect might be different across different categories of gender. And let's assume that this is that these are the estimates of the model. So 7.1 minus 1.4 multiplied by the female dummy, plus 0.4 multiplied by the middle class dummy, plus 1.3 multiplied by the higher class dummy, plus 0.7, so that's the first interaction term of the female dummy multiplied by the middle class dummy, plus 1.5, so that's the second interaction term multiplied by the female dummy times the higher class dummy. So notice here that I picked two reference categories, one for the gender dummy where I picked a male as the reference category, and one for the class categories where I picked lower class as the reference category, and distinguished between three levels of class, so lower, middle, and higher class. So that means that we get a main effect for gender with one dummy variable. We get two main effects for class, one for the middle class and one for the higher class, and we get two interaction effects of gender with class, one for gender, for the female dummy times the middle class, so that's the interaction effect for the middle class people, and one for female times higher class, so that's the interaction effect for the higher class people. And well, the easiest way to interpret this is, well, just calculate the predicted values for all the different combinations of gender and class that there are in our data, because there aren't actually that many. And that will show us exactly how that interaction effect, what that looks like. So we can do the predicted value, for instance, for the lower class men. Why I'm starting with the lower class men? Well, I picked men as the reference category, and I picked lower class as the reference category for class. So let's start with those. Let's start at, well, what is the predicted value for lower class men? And as always, challenge yourself before I do it for you. Maybe stop, pause, and think, can I come up with the right answer myself already? Yeah, but let's go through that. Well, let's walk through the formula. Predicted value for lower class men. Well, we start with 7.1. That's a constant. That's the same for everybody, of course. Then we get minus 1.4 times female, but these cases do not get the value 0 on female because they are coded as men rather than women. So they get the value 0 on the female dummy, which means that we would multiply that regression coefficient of minus 1.4 times 0, which works out to 0, which means you can drop it from the equation. And the same thing goes for the coefficient for the middle class dummy, because these are not middle class men, these are lower class men, so the middle class dummy would take the value 0 for these cases. Therefore, also this part of the formula would be multiplied by 0. And the same thing is, of course, true for the higher class dummy. That would also take the value of 0 for lower class men because they are not higher class. So also that regression coefficient of plus 1.3 would be multiplied by 0, which means that it's just 0 and we can drop it from the equation. The interaction term for female times middle class would also drop out of the equation because these cases would score a 0 on both the female dummy as well as on the middle class dummy because they are neither. So also this would drop out of the equation, and the same thing is also true for the last interaction term, so this 1.5 times female times higher class, because again these cases would score the value 0 on these female and higher class dummy variables, so that would be multiplied by 0 and would therefore also drop out of the equation. So in other words, what is the predicted value for lower class men? It's just a constant because that's the only thing we have left. So the predicted value for the reference categories is captured by the constant in our regression equation, which in this case is 7.1. Now let's look at, well, what is the predicted value for middle class men then? So for the next step up in socioeconomic class while still considering men. Well, again, let's run through the formula. 7.1, the constant, that's the same for everybody. Minus 1.4 times female is going to be multiplied by 0 because they score a 0 on the female dummy. So that would be a 0 and drops out of the model. The plus 0.4 for middle class we have to keep in the model because, yes, these are, as a matter of fact, middle class observations that we have here, these middle class men. So they would get the value 1 for the middle class dummy. So that would be plus 0.4 times 1 for them. They are not higher class. So the higher class dummy would take the value 0 for them. So that part of the model would also be multiplied by 0 and can be dropped from the model. They are not female, so they score value 0 on the female dummy, which means also that interaction term, even though they are middle class, they get this 1 on middle class, but that's then multiplied by 0, so that also drops out of the equation because that works out to 0, and the same thing is true for the last interaction term because they are neither female nor higher class, so they get 2 zeros here, so it's 1.5 times 0, which works out again to 0 and can be dropped from the equation. So in other words, the predicted value for middle class men works out to the constant value of 7.1 plus 0.4, so that's by how much higher the predicted value on trust in parliament is for middle class men compared to lower class men. It's higher by 0.4 points. So that means the predicted value for middle class men works out to 7.1 plus 0.4 is 7.5. And again, we can do the same thing for higher class men. The third class category for men, again 7.1, that's the same for everybody. Minus 1.4 times female would be multiplied by 0, so that would be dropped from the equation. Plus 0.4 times middle class dummy would also be multiplied by 0 because these are higher class men, not middle class men, so they get a 0 on the middle class dummy. The higher class main effect of plus 1.3 times higher class, of course, that we need to keep in the model because that 1.3 would be multiplied by 1 because these people are higher class, so they would score the value 1 on that dummy variable. The interaction term, however, again is going to be 0 because they score a 0 on the female dummy, in this case also on the middle class dummy, so that would drop from the equation, and the same is true for the last interaction term, so for the female times higher class interaction, because while they get the value for 1 for higher class, they get the value 0 for female, so that's multiplying something by 0 gives you 0, and we can drop that out of the equation as well. So in other words, what is the predicted value for higher class men? Well, it's the constant of 7.1 plus 1.3, the main effect for higher class. Yeah, so we now know that the predicted value for higher class men is 1.3 points higher than it is for lower class men, the reference category, which works out to a predicted value of 8.4. And then we can do the same thing for women. So we can see, well, what is the predicted value for, well, let's start with lower class women. Well, again, work through the formula. So it's 7.1 minus 1.4 times female. So that's the main effect for female. Well, these are women, so they get the value 1 on the female dummy. So that we actually have to keep in our model. So it's 1 minus 1.4 times 1. But they are not middle class, they are lower class. So the middle class dummy takes the value 0. So that part of the model is multiplied by 0 and can be dropped from the model. The same thing is true for the main effect of higher class, because they are lower class, not higher class, get the value 0. So 1.3 is multiplied by 0 and drops from the model. They get the value 1 on the female dummy and the value, but the value 0 on the middle class dummy. So also the interaction term between female and middle class can be dropped from a model because that works out to 0. And the same thing is true for the interaction with higher class, because again here they score a 0 on the higher class dummy, so that second interaction term also works out to the value 0. So what do we have left? We have 7.1 minus 1.4 times female for the lower class women, which means that the predicted value for lower class women is 7.1, the constant, minus 1.4, which works out to 5.7. So in other words, lower class women have a predicted value on trust in parliament that is 1.4 points lower than lower class men, the reference category. Yeah, so which works out to a predicted value for lower class women of 5.7. And again, we can do the same thing for middle class women. Run through the model, 7.1 minus 1.4 times female. Well, we have to keep that in the model. Plus 0.4 times middle class. Well, we also have to keep that in the model because these are in fact middle class women, so they score a 1 for the middle class dummy. But we can drop the 1.3 times higher class because they get the value 0 for the higher class dummy. We have to keep the interaction term, so plus 0.7 times female times middle class, because they score a 1 on the female dummy and a 1 on the middle class dummy. So that's 0.7 times 1, which just works out to 0.7. Yeah. But we can also drop the last part of the model, the second interaction term, because they score the value 0 for the higher class dummy. So the second interaction term is also multiplied by 0. So what is the predicted value for middle class women? Well, just walk through the formula. It's 7.1 minus 1.4, because that's the main effect for being female, plus 0.4, that's the main effect for being middle class, plus 0.1, that's the interaction between female and middle class, which works out to a predicted value of 6.8. 8. And lastly, we can do the same thing for the last combination of class and gender that we still haven't discussed yet, the predicted value for higher class women. Again, run through the formula. So it's 7.1 minus 1.4 times female. Well, they are women, so they get the value 1 for the female dummy, so that stays in the model. We can drop the next part, plus 0.4 times middle class, because they've scored the value 0 on the middle class dummy, because they are higher class women, so that gets multiplied by 0. The plus 1.3 times higher class remains in the model, because these are in fact higher class women, so they score the value 1 on that dummy variable, so that's plus 1.3 times 1, which works out to just 1.3. We can, however, drop the interaction term between female and middle class, because they are not middle class, so the middle class dummy takes the value 0, so that interaction term works out to 0, but we need to keep in the 1.5 times female times higher class, because they are both female and higher class, so that means that what value would these observations get? Well, 1.5 times 1 times 1, which works out to 1.5. So again, what is the predicted value for higher class women? Well, just add up all the individual terms in our model that are still relevant. So that's 7.1 minus 1.4, the main effect for the female dummy, plus 1.3, the main effect for the higher class dummy, plus 1.5, the interaction term of female times higher class, and we get a predicted value for higher class women of 8.5. So now we see that our model gives us predicted values for all possible combinations of age, of gender and socioeconomic class that we considered in this case. Yeah, so that's great. Of course, you might say, well, I get all these different predicted values. So now how do I interpret that? Well, one thing that you could, of course, always do is, well, just make a graph of the predicted values. So I did this in this case. You could do this manually. You could use SPSS to do that. I used Excel to do it. So I just plugged in the predicted values for all these different combinations of gender and socioeconomic class. And then I just drew a nice little line graph. So I made 2 lines. So that's on the x-axis, I put the middle, the class effect. On the y-axis, the predicted value on trust in parliament. And then I made 2 lines, one for a male and one for female. And then I plotted all the relevant predicted values for the different levels of socioeconomic class. So in this case, you see that there is a positive effect of socioeconomic class on trust in parliament. But that effect is actually more pronounced for women than for men. So for men, we see that we start already with a higher value among the lower class men, because we included the main effects, of course, allowing basically for there to be a difference there. But then we see that if we go from left to right, from lower to higher class, it doesn't make so much of a difference for men. But for women, because they had a fairly low starting out point, we see that there's much more of an effect, a much more pronounced effect. So there's quite a bit of interaction going on between class and gender. But again, these are completely fictional data, so if you want to find out whether that's true for real data, well, do it yourself with the European Social Survey or any other data set that measures these variables and check it out. Yeah, so that's how to help yourself interpret all these different predicted values. Well, just make a simple graph. I think there is also an Excel sheet or a link to an Excel sheet on Brightspace that you can also use for that, which does that in a bit more fancy way for you and doesn't require you to do everything manually yourself, but just fill in the right values and you automatically get a nice graph. So I would recommend taking a look at that. Now, that's for working with categorical X variables. Let's do a little bit of mathy stuff. Not too much, not too brutal, but basically the most intense that it's going to get during this course in terms of math, because there's a couple of things that you probably have heard about in your prior education, but it might be quite a bit mystic, a mystery to you by now, or maybe you've forgotten a lot about it and maybe you didn't hear about it. So it makes sense that we very briefly just discuss some basic math before we move on, because we need to have at least some kind of understanding of these things. So I'm going to talk a little bit about exponential and logarithmic transformations. Yeah, so let's start with exponential transformation. So what is exponentiation, other than a really great word to use in everyday language? What is exponentiation? Well, exponentiation is a mathematical transformation that takes the following general shape. We have some number b, we have some number n, and that gives us some result x. So why b, why n, and what is x? Well, b stands for the base number. So that's the number we are going to start out with. So we call that the base number, and that's why we're using the letter B to indicate, well, this is the base number, the number that we are starting out with. And what is the n? Well, the n is the exponent. So the exponent is the number we plug into n, which indicates by to what power we are raising our base number. To what power we are raising the base number that we start out with. In other words, how often do we multiply the base number with itself? Because that's taking something to some power means multiplying that value with itself as many times as there are in the exponent are captured by the value of the exponent. Yeah, so we have a base number that we start out with, and we're going to exponentiate that with some exponent, and that is going to give us some results, some resulting number, and that's the number x that we get. So that is basically fundamentally what exponentiation is. We have some base number b, we raise that to the power of some exponent n, and that gives us a resulting value of x. So let's look at a couple of simple examples. So if we take as a base number the value 2, and we take as an exponent also the value 2. So in other words, we say 2 to the power of 2, or to the second power, or as it's more commonly referred to, 2 squared. Yeah, so 2 is our base number. In this case, 2 is also our exponent. So we pick 2 as the base number and we pick 2 as the exponent. So taking 2 to the second power. Well, stop and think for yourself. What is the value for x? Great, you probably figured this one out. 2 to the power of 2 means that we are multiplying 2 with 2. Yeah, so it's 2 times 2. Well, what is 2 times 2? That's 4. Yeah. Why multiplying 2 by 2? Well, we picked 2 as the value for the exponent. So we are multiplying the base number with itself. Yeah, so that's 2 times 2. Right, so that's 4. Let's look at a different example. Let's say we pick as the base number 5, and we pick as the exponent the number 3. So in other words, we are taking the number 5 and we are raising that to the third power, or in common language, this is sometimes referred to as cubing a number. Yeah, so 5 to the third power. Well, what is the value for x if we take 5 to the third power? So if we pick the exponent 3 for the base number 5. Maybe some of you figured it out. It's 125. Why is it 125? Well, 5 to the power of 3 means what you're saying is 5 times 5 times 5. So 5, that's the first one, times 5, that's the second one, times 5, that's the third one. Well, 5 times 5 is 25, and 25 times 5 is 125. So 5 to the power of 3 to the third power works out to x equals 125. One more, 6 to the fourth power. Well, there's no nice common language way of referring to taking something to the fourth power anymore, so we just have to stick with 6 to the fourth power. But yes, we pick as a base number as 6, and we pick as an exponent 4, so we are taking 6 to the power to the fourth power. What is the result of that? If you were able to figure this out without a calculator, you are much better at math than I am. It works out to 1,296. 96, yeah. Why? Well, it's 6 times 6 times 6 times 6. Yeah, so 6 to the fourth power. How the exponent tells us, well, how many times do we multiply the base with itself? Well, 4 times. So it's 6 times 6 times 6 times 6, which works out to 1,296. Yeah, so that's what exponentiation is. So why do I talk about exponentiation? Well, for one thing, exponential transformations can be useful for linear regression models, as I will show you in a little bit. But there is another reason I'm showing you exponentiation first, is because one thing that's really important that we understand is another type of mathematical transformation, the logarithmic transformation. And the easiest way to understand what the logarithmic transformation is to know what the exponential transformation is, or what exponentiation is, because logarithms are basically just the reverse of exponentiation. Yeah, so it's basically just doing the reverse of what we would be doing when we exponentiate something. So if exponentiation is captured by this formula of we have a base number b and an exponent n, and that gives us some result x, then taking the logarithm of a number is basically reversing that logic. So taking the logarithm of the number is finding the value that we need for the exponent with some given value for a base number to get a certain value x. Yeah, so we say we have a log, so log is a short for logarithm, of some base number. And for that base number, we want to get from that base number to the value x. And we need to find the right exponent to get to that value x. So in other words, the logarithm tells you, well, to what power would I need to raise b in order to get some value x? Yeah, so that's what the basic logarithmic function gives you. So in other words, how often would I need to multiply the base with itself to get to some value x? Yeah. Again, best way to understand it is probably to look at a couple of examples. So let's see, I pick as the base number 2, and I want to get to the value 8. Yeah, so I want to figure out, well, to what power do I need to take 2 in order to round up with the result of 8. Yeah, so in other words, what I'm trying to find here is the log base 2 of 8. Now, as always, stop and think for yourself first. What is log base 2 of 8? So to what power would I need to take the base number 2 in order to get a result of 8? Some of you probably gave up on that one. Some of you might have figured it out. It is 3. Why is it 3? Why is a log base 2 of 8? Why is the result of that 3? Well, it's saying, well, we have as a base number 2. So we need to think about, okay, to what power do we need to raise 2 to get the value 8? And that is the power 3. Because 2 to the power of 3, so 2 cubed, means that we say 2 times 2 times 2. So 2 times 2 is 4, times 2 works out to 8. So we need to raise 2 to the power of 3 in order to get the value 8. So log base 2 of 8 works out to 3 because that's the value we need to plug in for the exponent to get from 2 to 8. Let's practice once more. So let's look at what would be the result for log base 5 of 25. So in other words, we're picking 5 as the base number. And we want to figure out, well, to what power would I need to raise 5 to get the result of 25? So what is log base 5 of 25? To what power do I need to raise 5 to get 25 as a result? It is 2. Why is it 2? Well, 5 times 5 works out to 25. So if we raise 5 to the power of 2, we get 25. So the log base 5 of 25 is 2, because that's the power we need to pick to get from 5 to 25. One more. Log base 3 of 27. So we pick as a base number 3. So in other words, and as x we pick 27. So in other words, to what power do we need to raise 3 to get as a result the value 27? And it is 3. And why is it 3? Well, 3 times 3 works out to 9. And 9 times 3 works out to 27. So 3 times 3 times 3. So 3 to the power of 3 works out to the value of 27. So in other words, we need to raise 3 to the power of 3 to get the value 27. So log base 3 of 27 equals 3. Yeah. So that is natural logarithms in general. Now there is often a very specific type of, that's logarithms in general, and there's often a specific type of logarithms that we tend to work with a lot, and that's the so-called natural logarithm. So that's often written as log with the little e, or sometimes as ln. The n stands for natural and the l stands for logarithm. Both of these things both of these ways of writing it mean the same thing. That's the idea that we are going to take the natural logarithm. And what makes the natural logarithm special compared to other types of logarithms, it is what we use as the base number. Because with natural logarithms, we don't just use any number for the base number, but we're going to use one specific number. And that number is the so-called Euler's number. So that's a very specific number, often indicated with this little e letter. One of the people that was fundamental in showing all the great mathematical properties of this number is Euler, so it was named after him. And and it is a number, even though we use a letter, but it's an irrational number. So it is rounded. It works out to round about 2.718, and then lots and lots more of numbers behind the comma. But this is the number that we use when we use a natural logarithm. Now, you don't need to worry about why do we use this specific number, at least not for this course. It has all kinds of nice mathematical properties that makes life a lot easier if you have to do mathematical stuff with it, and it makes also the interpretation of the outcomes of that stuff very nice. But for you, it's just enough to know that if we talk about natural logarithm, we talk about a logarithm where we pick this Euler's number as the base number, and that Euler's number works out to around about 2.718. So in other words, what is the natural logarithm of a number? It is the value that we would need for an exponent with this base number, this 2.718 as the base number, this Euler's number, to get to a certain number. So it's basically doing a logarithm like we would normally do. The only thing that we are now pinning, saying, well, this is always the same, is the base number, and that base number is then always going to be Euler's number. And quite often it can be quite useful to use these natural logarithmic transformations on our variables. And later we'll see that this is going to come back when we do logistic regression as well. There's a couple of things you need to be aware of if you want to take natural logarithms. One is you can only do that for numbers that are larger than 0, positive and larger than 0, because there is no way to, there is no solution for Euler's number to some power that will give us the value 0. And there is also no way of raising this Euler's number, this 2.718, to any power that will give us a negative result. So in other words, whatever power we raise this Euler's number, this 2.718 to, we will always get a positive number. So natural logarithms can only be calculated for positive numbers, not for 0 and not for negative numbers. And it's just something that's useful to be aware of if you want to use natural logarithmic transformations, that this only works if your variable only has positive numbers. Well, let's take a look at, well, why would you want to do that? What do these transformations bring us? Well, let's look at what is the relationship between a variable and the exponential transformation of that same variable. So here I used an Excel sheet and I just plugged in different values for some variable x. Yeah, so just steps of 1 on our x variable going from 1 to 20. And then I created a new variable where I took the exponential transformation with base number e, with this Euler's number as the base number of that original x variable. So I created a new variable, and that's the exponentiated version of x. And then I just plotted, well, the values of x on the x-axis and the corresponding value of the exponentiated version of x on the y-axis. And you will see that, hey, that's an interesting relationship. So it's going up, up, up very little, and then increasingly so, and then increasingly so, and increasingly so, and then increasingly so. So basically the relationship between x and the exponentiated version of x is one that is not linear, obviously, so that's not a straight line. It is a relationship that is monotonic. So monotonic meaning that whenever our value of x goes up, of our x variable, the exponentiated transformation of x is also going to go up. So higher values on the original x variable also mean higher variables on the exponentiated transformation of that variable. So whenever x increases, the exponentiated version of x also increases. So that is what we mean when we say that this is a monotonic relationship. So if one goes up, the other always goes up as well. But it's definitely not a linear relationship. It is a relationship where we see, well, as x increases, the exponent of x increases, but at an increasing rate. So the more we increase our x variable, the faster the exponentiated version of x is going to increase. So we could do that for ever higher values. You would see that this line is becoming ever steeper, ever steeper, ever steeper, ever steeper. Yeah, indicating that the exponentiated version of our variable grows at an increasing rate if our original x variable grows. So that's a transformation that can sometimes be quite useful. So for instance, let's say you expect your x variable to have an effect on your y variable, but you don't think it's a linear effect. You actually expect that it's an effect where the higher the values of your x variable are, the faster the predicted value on your y variable increases. Yeah, so you get this effect where you say, well, it's not just that it's increasing, but it's increasing at an increasing rate. So the higher the values of x are, the faster my predicted values are increasing. Well, if you have that kind of relationship that you want to model, maybe because your theory predicts it, then you could just include a exponential transformation of your x variable instead of the original x variable to capture this exponential relationship. Yeah, so that's that can be quite useful. If you look at how are values related to the natural logarithms, then this is the picture that we would get. So again, I used an Excel sheet and I just plugged in different values for some x variable. So in steps of 1, I plugged in values from 1 to 100, and then I created a new variable which takes the natural logarithm of those same values and put that on the y-axis and the original values on the x-axis. And this is then what the relationship is between the original variable x and the natural logarithmic transformation of that variable. And again, here you see that it is not a linear relationship. Yes, we see that as the steps in which the logarithm of x increases are not always equal for every step on the x-axis. But it is still a monotonic relationship, meaning that it's still the case that if x goes up, the natural logarithm of x also always goes up as well. Yeah, so a step up on the x-axis also means a step up on the y-axis, but it's not the same step always. It is an increase where we say, yes, as x increases, natural logarithm of x increases, but at a decreasing rate. Yeah, so here we see that the higher the values are of our x variable, the slower the increase are of the natural logarithm of that x variable. Yeah, so we start with quite fast increases for low values of the x variable, and then the further we go, the higher we go on the x-axis. So the higher the values of x variable are, the slower the increase is on the natural logarithm of that x variable. And again, here that can often be useful if you, for instance, expect there to be some effect of your independent variable on your dependent variable, but you expect that effect to be very large for low values of your x variable, but then become smaller and smaller and smaller the higher the values of your x variable are. Yeah, so if you have that kind of situation, you could say, well, maybe I'm going to, instead of using x, I'm going to use the natural logarithm of x as my independent variable in the regression model, because that would allow you to capture such a relationship. Yeah, maybe you say, well, I'm interested in analyzing the effect of economic development on democratic development, but I expect that that effect will be quite large for countries that have a relatively low level of economic development. So for relatively poor countries, it makes a lot of difference. There's a fast increase in the level of democracy for every increase in economic development. But the richer countries become, the less of an effect it makes. So the less quickly the predicted value on the level of democracy is going to increase with further increases in economic development. So if you have that kind of situation, well, whatever variable used to measure economic development, so for instance GDP, well, take the natural logarithm of GDP and include that in your model rather than the original GDP variable to capture this logarithmic relationship. So exponentiating and taking logarithms can be quite useful if you want to capture these kind of relationships that are exponential, so increasing at an increasing rate, or logarithmic, so increasing but at a decreasing rate. Yeah, so for that it can be quite useful. I've put the Excel sheets that I used to make all these figures up on Brightspace, including some couple of extras to allow you to really understand, well, how would that work if I would put these things into a regression model. So you can check that out for yourself. Related to that, in the A lecture I already talked about how we can use dummy variables if we have variables that we treat as continuous variables, but we worry about, well, does it really make sense to think of these variables as having a linear effect, or might they have an effect that there is some kind of effect, but it's not a linear effect? Yeah, so this is what I already hinted at in the A lecture, that you can use dummy variables sometimes in this situation. As a matter of fact, I did just such a thing. So I used some old European Social Survey data. I think it was the ESS Wave 8, and I had satisfaction at the national government as a dependent variable, and I estimated the income effect, so using deciles of household income. So then we have these 10 deciles of household income. But I was kind of worried about, but does it really make sense to have a linear effect for income on satisfaction of government? Because that presumes that for every one step we go up on the income scale, the change in the predicted value on the satisfaction of national government is always the same. That might not necessarily be the case. So estimating a linear model means that we assume a linear additive effect, and maybe that's not the case. Maybe income doesn't have this nice linear effect. And so because income only has 10 categories, I figured, well, what I'm going to do is I'm just going to make dummy variables for all the different income categories except for the lowest one, because I'm going to use that as a reference category. And instead of having one linear income effect, I'm just going to treat income as a categorical variable, and then include 9 different income dummies into my regression model. Yeah, so that is the regression model that I got. So notice satisfaction of national government was a dependent variable, and I have a dummy variable for the second income decile, the third income decile, the fourth, the fifth, the sixth, all the way up to the 10th income decile, where the first income decile, I use that as the reference category, so that is captured by the constant value of the regression equation. So why did I do that? Well, because I wanted to check, does it make sense to use a linear effect for income? Because if it makes sense to have a linear effect for income, that means that every step on the income scale should lead to the same increase in the predicted value on satisfaction of the national government. And because I now created dummy variables, I can check whether it's actually the case in my data. Because that means that if I use dummy variables for the different categories of income, then those dummy variables should show me that it is indeed the case that the predicted value on my dependent variable increases in roughly equal steps. So that means that for every step up on the income scale, the predicted value should increase by more or less an equal amount, because only then I can say, well, okay, then it actually makes sense to just use a linear effect, and I can just do that. Yeah, so using these dummy variables can also be a way to just check up on that. So in this case, I estimated this model, and then to visualize it to myself, I just plotted the predicted values from this model on the y-axis across the original income scale. So now we see that we get a different predicted value for each category of household income. Yeah, so this is the predicted value for the first category of household income. In other words, what's the constant value in our regression model? This is the predicted value for the second category of household income, so the second decile, so that's the constant value plus the regression coefficient for that dummy variable for the second household income decile. This is the predicted value for the third household income decile, so that's the constant value plus the regression coefficient for that third household income decile, and so on and so forth until I have all the 10 household income deciles. And now I can actually visualize that. To what extent does this change in predicted value, is it really always more or less the same, and does it look like a linear effect? And here you say, well, it's not always perfectly the same, definitely not. So we see that here, for instance, the increase from the first to the second decile is quite a bit bigger than from the second decile to the third decile. That's a bit smaller of an increase in predicted value, but then from the third to the fourth, that's a big increase again. And there's a more or less similar increase for the fourth to the fifth decile, and from the fifth to the sixth decile, that's also more or less the same. For the seventh decile, we actually see that the predicted value is actually a little bit lower than for the sixth decile, but then it increases quite a bit again for the eighth decile, and it increases quite a little bit for the ninth, and a little bit on top of that for the 10th income decile. So is this now, would you now say, is this a linear effect? Well, yeah, kinda. So more or less we could say, well, if we would just want to capture all this overall relationship, then a linear line actually isn't terrible to represent this overall relationship. It is more or less a monotonic relationship. So we see that mostly it is the case that as income goes up, the predicted value goes up, except for this one 7th decile household income category, and the linear line would probably not be terrible. So I could say, well, that gives me some confidence that I could switch, that I could use the linear model. But you could also say, well, yeah, but if you look at that, you see that the effect of household income is monotonic, but it tends to be really, really large here. So from going from 1 to 2 and from 1 all the way up to 6, we see a fairly sizable effect of income. But then if you look at the highest categories of income, it doesn't seem to make such a difference anymore for our predicted value. So it's a bit of a relationship I would say, well, it's a positive relationship overall, but it seems to taper off a bit. It seems like differences, increases in household income lead to large increases in the predicted value on satisfaction with government for low household incomes, but the further we go up in household income, the less of a positive impact household income still has. So yes, the predicted value increases with household income, but at a decreasing rate. In other words, I could try, maybe, if I see this, to instead of using the linear income effect, use the natural logarithm of income instead, because then I do probably get a bit closer to the true relationship, so allowing for that effect of income to taper off a bit for very high income categories. But at the same time, I don't need to include all those different dummy variables in my model as well, because of course that is also asking a lot from the data that we're estimating. And then if you want to include more X variables, at some point we run the risk of overfitting our model again. So especially if you have a small data set, you might then say, well, okay, now I checked, this is what I can learn about the overall effect. Maybe try, in this case, a logarithmic transformation of income, and then compare that to the linear model, also compare whether the goodness of fit might be better with logarithmic transformation. Of course, does it make sense with the theory that you are expecting this tapering off income effect? But if that's the case, you might want to instead then use the natural logarithmic transformation. So I put the syntax comments that I used to do all of this, and all my reflections in the comments of those syntax comments. I've put all of that on Brightspace, so you can check that for yourself sometime. Do note I used the ESS 8, not the ESS 9 to do that. So you would need to download the ESS 8 to get exactly the same results as I did. But that's useful sometimes to have these natural logarithmic transformations of our X variables if the linear effect isn't maybe such a great representation of the true effect, and we have an indication that maybe logarithmic or maybe even an exponential transformation is a better fitting with the effect that we have in our data. So that's on that. The last thing I want to close off on, where we talked already about probabilities and odds, I want to introduce one more concept, log odds, and I want to talk about the relationship between probabilities, odds, and log odds. So if we look at probabilities, well, we know that probabilities can go from 0 to 1. So things can't happen less often than never and can't happen more often than always. So probability always has to be some value between 0 and 1. So I made an Excel sheet where I just plugged in different potential values for probabilities ranging from 0 to 1. And then I calculate the corresponding odds for those probabilities. So I took every probability and I calculated that probability divided by 1 minus that probability to give me the odds. So that was the second variable in my Excel sheet, and then I just made a graph where I put the original probability on the x-axis and the odds on the y-axis. And so this graph shows us, well, what is the relationship between probabilities and odds? And you see here that the relationship between probabilities and odds is a monotonic relationship. So as the probability goes up, the odds also go up. But you also see that the relationship almost kind of looks like an exponential type of relationship, where you see that as the probability increases, the odds go up a little at first and then ever more and ever faster. So basically here you can also nicely see how probabilities run from 0 to 1 and the corresponding odds grow along with that. But the further you increase the probability, the more your odds go towards infinity. So the closer I move my probability value to that 1 value, the more this line is going to go steeper and steeper and steeper and steeper up until basically we go towards infinity. So this is good to know, that this is the relationship in probabilities and odds. As probability increases, odds increase slow at first and then increasingly fast. So the higher your probability is, the relatively higher your odds are going to be. We could also plot the relationship the other way around. So instead of putting the probability on the x-axis, we're going to put it on the y-axis and put the odds on the x-axis. And then it's just, of course, the same relationship flipped around. So then we see that as our odds go up, the probability increases the corresponding probability increases very, very quickly at first. And then the further we move up our odds, so the higher our odds are, the slower the increase in our probability becomes. So this is this kind of small letter R shaped relationship between odds and probabilities. Because of these underlying relationships, between probabilities and odds, there is another thing that we can do, is we can, instead of looking at the odds, we can look at the natural logarithm of the odds. So whatever the value is for the odds, we can take that value and take the natural logarithmic transformation of that value. And if we were to do that, we often refer to the resulting number as the so-called log odds. So log odds is a short way of talking about the natural logarithm of the odds. So the natural logarithm of p divided by 1 minus p. And again, here I made a nice little Excel graph where I put the probability on the x-axis and the corresponding log odds that belong to that probability on the y-axis. Yeah, so log odds are basically a double transformation of the probability. First, we transform it from a probability into the odds, and then we transform those odds into the log odds by taking the natural logarithm of those odds. And if we would look at the corresponding relationship between the original probability value and the corresponding value of the log odds, we get this kind of snaky relationship. So we see that for probability values that are smaller than 0.5, yeah, so the event happens in less than half of the observations, we get a log odds value that's negative. And for probability values that are larger than 0.5, so the event happens in more than half of the cases, we get a positive value for the log odds. And if we look at the exact relationship, we see that we start with a very negative value for the log odds that increases as we increase the probability, at first quite quickly, and then slower and slower and slower, and then until we are at the way around the halfway point, and then we get to a positive number for the log odds, and then it increases and faster and faster and faster and faster again. So that's the relationship between probabilities and log odds. And again, we could flip the axis around. So instead of putting p on the x-axis and the log odds on the y-axis, I could also put the log odds on the x-axis and p, the probability, on the y-axis. So it's the same relationship, just switching the axis around. And then we would get this great, awesome, interesting relationship where we can see that if we look at how are log odds related to probability values, we see that for super low probability values, we start with negative log odds, as we already saw. And then as the probability goes up, the log odds increase increasingly fast, and then they increase even further, and then they start increasing slower and slower and slower again. In other words, if we transform probabilities into log odds, we get a relationship between log odds and probabilities that is shaped like the letter S. So this is an S-shaped relationship. Now you might think about, okay, that's great, neat trick. Why are you showing me this? Well, knowing this is going to come in really useful next week, because next week I'm going to show you how you can use this double transformation from a probability into an odds and from an odds into a log odds as a trick to be able to analyze categorical dependent variables, because that's the trick that we are going to use, which is referred to formally as logistic regression analysis. We are going to be transforming our dependent categorical variables from probabilities into log odds, exactly for the reason that we see here, that we then get a relationship between log odds and probability that follows an S curve. And next week we're going to see why it's important to have this double mathematical transformation available to us, so we can translate log odds values into an S-curve relationship with the underlying probability value. Yeah, so it's important that you at least are already aware of what that relationship looks like, and then next week we are going to put it to some very good use. As always, all this stuff, the Excel sheets, as well as syntaxes that show you how to do this stuff, all of that is on Brightspace. You can take a look through that yourself to make sure that you really understand it. And if you have any kind of questions, comments, whatever, please come as always to the Zoom sessions. We are there to help you. We are there to assist. But of course, you need to come and you need to actually ask questions if you have them. Yeah, so hope to be seeing you on Zoom. Bye bye. Ciao, ciao.